Okay, so actually I have some bad news and good news. The bad news is that the world is unfair, but the good news is that there's something we can do about it if we work together. So let me put that in the context of machine learning, where we have the features and we train some classifier to predict the labels. After training, we measure the accuracy and we are satisfied with the accuracy. But here's the twist. This classifier might actually affect people's lives. Maybe it predicts whether it will default on the bank loans, or maybe it predicts some medical treatment. So we really need to be careful here. And when we study the results a bit more, and for example, we split the data into a majority group and a demographic minority, we notice that we still have a high accuracy for the majority, but we have very, very low accuracy for the minority. This type of bias can be categorized in the fairness literature as group fairness, where we want a classifier to give us similar outcomes to different demographic groups. In this case, the outcome is the accuracy, but there are many different metrics and definitions for what an outcome is. And there's plenty of research on how to fix fairness in machine learning, and all of them basically focus on changing the learning algorithm or pipeline. So you might want to edit the data a little bit or post-process the results. And all of these things do improve fairness, but a very known result is that it also lowers the predictive accuracy of your model. So put yourself in the seat of some big company who wants to just maximize profit. So sure, they have some fair learning algorithm they can use, but if you have higher errors from those algorithms, then it can translate to lower profits. So if you want to maximize profits, you might not want to adopt those solutions. But that's not the end of the story, because we need to remember that many companies today, they train on data that we users give them. We provide the data for them. So if users have agency over the data that the model trains on, then can a minority induce fairness through the data? This type of question is studied at another field called algorithmic collective action. In this setting, we have a classifier that is trained on data that is generated from the end users. So there are actually no access to any point of the training pipeline. Only each person can modify their own data that they provide to the dataset. So if one person changes their own data, you will not see much of an effect. But if a lot of people work together and coordinate how to change the data, then we might see a big effect on the classifier. So this type of work asks what can they do, how many people do you need, and is the success guaranteed? So this is pretty abstract, so let's get into a more concrete example and think about an example where the collective, a group of people, want to work together to make some classifier ignore a signal G. So let me put it formally. We have the success of a collective. The collective is a group of people who are a fraction alpha of the whole population that work together. And for some classifier H, they want the outcome for X to be the same as G of X. So G is some transformation of the data. And because we want the outcome to be the same, it's sort of like ignoring the signal G. And if you want some guarantee over the success, then one strategy the collective can employ is that every member of the collective will flip their labels, or change their labels according to the most probable label if they would have transformed their data under G. So let's pause it a bit, because this is a lot of things and very confusing, and I just went from fairness to collective action. So let me present the hypothesis that we had that combines the two. So we ask, if G, the signal that we want to ignore, encodes some information about the group membership, then the classifier might ignore the group bias. And this essentially might translate to fairness. So the plan is, first, we need to figure out how to make G encode group membership information. Then we need to deploy collective action. And then we need to see if we actually get some group fairness as a result. And to make G encode some group membership information, naturally, we go to causality, and we assume a very simplistic causal model. So you don't really need to know causality. Just know that we have some group membership that is some causal parents, and basically all the other causal parents are aggregated in U. And this generally gives us a set of features and labels. With this very simplistic assumption, we can define G to be a counterfactual signal, where G of X essentially changes the group membership causal parent to be from the majority. So it's sort of a counterfactual question. What if we take someone and make them be from the majority? How would that change things? So with this signal, we can now employ the strategy from before, where we take the most probable label under this transformation. And this gives us already two problems. First, we don't know how to compute counterfactuals, or at least not well enough. Second, maybe the majority members don't want to participate. Maybe they want to keep the status quo, so they don't want to be active. So we limit ourselves only to the minority. So we do slight changes to the method. And what we do is first, we pull together all the minority members who have negative labels. Of all of those, we estimate the likelihood of having a counterfactual positive label if they came from the majority. To do that, we have also some three simple methods. Either we use some regressor on the majority and we take the results on the minority, or we look at the k nearest neighbors of the majority for each individual in the minority, and either count how many positive labels are around or the distances to the positive neighbors. Each of those methods give us some score, and we use these scores to basically sort the candidates. And then the candidates with the highest scores, they are the ones whose label we flip from negative to positive. And that's basically it. So now the question is, does it actually improve group fairness? So I will present two of the main results in the paper. The first is what happens if as the collective size increases. So on the x-axis, we have the fraction of the minority that participates in the collective action. And on the y-axis is something called the best equalized odds. Equalized odds is a metric in group fairness that compares the true positive and false positive rate between the two different demographics. And we want those differences to be as low as possible. So the lower the score is, the more fair the classifier. So the red line is the basic classifier. You just train it on the data without any collective action in it. And the three lines are basically our three methods I showed before. And you can see that as the collective size increases, fairness improves linearly until it saturates at around between 20 to 30%. And we found this is consistent across all the data sets we tested on. Next, we wanted to see how it compares with firm-side methods, which are more common. So we tested against fair and calibrated equal odds, which are the green and yellow lines. And here we compare the trade-offs of fairness and error. So essentially we have the error on the x-axis and the fairness on the y. And the more lower and to the left it is, the better, because it has less error and it's fairer. And we can learn two things from this figure. First, that generally collective action, minority collective action, cannot achieve perfect fairness. So perfect fairness will be here at the zero line. And we see that the firm-side methods, the classical methods, can achieve zero, but the collective action cannot. But on the other hand, the error you get from collective action is much, much smaller than the error you get from the two firm-side methods. And this is, again, something that is consistent over all the datasets we tested on. So due to not much time left, I will recap now. And the idea of the whole project was to use the collective action framework for fairness. So we take the shift from firm-side methods to something that users can do themselves. And we show that fairness, it does improve linearly with the collective, the bigger the collective is, until it saturates at some point, because generally it cannot achieve perfect fairness. But again, they have much smaller error than the firm-side methods. So if you want to read more details, see some more experiments done that we really looked into each method into more details, or read some theoretical guarantees, you're welcome to read the preprint or ask me at any point. So thank you very much for listening.